Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's our pleasure to have Tal Malkin speaking today. Tal is a professor at Columbia, and she's well known for work on black box separations of cryptographic primitives and multi-party computation. And today she'll be speaking about public key cryptosystems.
Thanks. Okay, so hi everyone. First of all, I understood my initial announcement said I'm a CEO of something, so I'm not. If you want to leave the room now, it's okay. And I'm going to talk about a line of research. It has several different works within the same line of research that is about making public key cryptosystems stronger. I wasn't sure who the audience would be, so I will try to make it general without too many technical details. And I have millions of slides to go into if you have questions at the end or you want to talk to me afterward. OK, so here is the outline of my talk. I'll start with a 4-slide version of the entire talk. And then I'll move on to a many-slide version of the same talk. OK, so we're starting with a 4-slide version. So public key encryption, I know you all know what it is, but let me go over it both for consistency and for motivation. So public key encryption, the idea was given by Diffie and Hellman in the 70s. And the idea is basically, informally, Alice and Bob want to communicate securely over an unsafe channel. Okay, and the whole point of modern cryptography started from defining really what does it mean to communicate securely, what does securely mean, and what does an unsafe channel mean. Okay, so basically showing that you can in fact define it rigorously and you can in fact achieve these definitions by constructions that provably achieve the definitions, typically relying on some assumptions, okay, like factoring is hard or anything else. The point is the assumption needs to be well-defined, well-understood, easy to refute, easy to study, etc. Okay, so the first such definition of security was given by Goldwasser and Micali in '82 of something they called semantic security. Okay, and for them, the red is kind of what securely means, and the blue is kind of what unsafe environment means, or how is it unsafe. So for them, they define security as secrecy. Okay, namely, you hide your message against a passive adversary, an eavesdropper. Okay, and this is called semantic security, and already is hard to define and hard to achieve, but they did it in the 80s. Okay, however, as cryptographic applications become more prevalent, and there are many different settings, this kind of security is no longer enough for many applications. Okay, just a passive adversary is just not enough. So this is a list of stronger attacks. I could list more, but these are the attacks I have solutions for. These are attacks that are stronger than just a simple passive adversary. Okay, and we want to protect against them as well. So for example, this is all at this point not informal. So let's assume the adversary is not just a passive eavesdropper who sees what you send over the line, but for example, what if the adversary can change the ciphertext while it's in transit? Okay, that's a man-in-the-middle attack or malleability. Or what if the adversary can actually get to the decryption protocol, has access to your decryption protocol? Can he learn something? That's called chosen ciphertext attack. There's an adversary that can adaptively, an adaptive adversary is somebody who can, let's say some protocols are running, the adversary will see what's going on, and based on that will decide where else to break into. Okay, that's a strong adversary. You could also, all the previous, or at least in the 20th century, all the cryptographic algorithms assumed some secret key, say, on which all the security relied, and the secret key is assumed to be totally secret. Okay, but that's not really realistic. The secret key might leak either by malicious insiders or stupid people, or by side channel attacks, or all kinds of ways the secret key could leak, or the secret key could be changed with some tampering attacks. So all these are strong adversaries that are not captured by the previous notions of security, by semantic security. Okay, and we want to protect against them as well. So this line of work I'll be discussing is about protecting against these stronger attacks. And I'll focus specifically on public key encryption, although in general this approach could be defined for many cryptographic tasks. So this is our goal. Number one goal is to secure against as stronger attacks as possible. However, we would like to do it with the following principles. So first of all, we want to do it based on the most general possible assumption. Okay, so what does it mean, most general possible assumptions? I told you that everything, when you prove security, you need to assume something. Okay, we want to assume as little as possible. Okay, the best case that we would like to achieve is if you start from an encryption scheme that's known to be semantically secure, namely it's only known to protect you against passive adversaries, can you do anything in order to make it secure against stronger adversaries without adding any extra assumptions, any extra anything? I mean, you might change the protocol, but the proof of security will not need any extra assumptions. This is clearly the minimal one, right? When you start with a weaker one, we call it immunize. You can immunize it to get stronger security without any extra assumption. Okay, so that would be one goal, to have as small assumption as possible. And the second goal would be to use the underlying primitive in a black box fashion. So what does it mean? What is this underlying primitive? Let's say this is what I do. I start from semantically secure encryption, namely weak passive encryption, and want to achieve some strong encryption. Okay, so I would like to use the weak encryption, the semantically secure encryption, in a black box way. You can think of black box way as something, as a subroutine. Okay, I don't need to know anything about what's going on. I don't want to assume any algebraic properties. I don't know my homomorphism, some field properties. I don't want to assume any of this. I want to assume I have a black box. I have a subroutine that is guaranteed to be semantically secure. Can I use it to have guaranteed strong security? Okay, so I don't know if you were counting, but this was the third slide and the fourth slide version of the talk. So I just wanted to motivate why did I come up with these two requirements. Obviously, I think the first one is clearly well motivated, that we want to protect against stronger adversaries. Why do I want weak assumptions in black box fashion? So this is interesting both theoretically and practically. So, and even these bullets, I don't even know which ones are practical and which ones are theoretical. They both are a mix of all. But we want to achieve as minimal assumption as possible in a black box construction for several reasons. One, it will really give us insights into the primitives. And so this is like complexity theory for cryptography. Okay, which primitives can be reduced to which? Is this assumption sufficient for that? So, and you know, what is it that you need to assume? So, when you have both, so this second bullet, more possible instantiation, refers both to the black box and to the minimal assumptions. So clearly, one obvious reason we want to minimize assumptions, that's a well-known goal in cryptography, is that we want our systems to be secure. Okay, so if I only did a system based on one specific assumption, I don't know, maybe tomorrow somebody will break that assumption, and it won't be secure anymore. So clearly, I want as weak assumption as possible. If I could, I would like to do it without any assumption, but that is not possible for public key encryption and for most cryptographic primitives. So I want security to be possible under any possible instantiation. Okay, so if somebody believes in elliptic curves and somebody else believes in hardness of some lattice problems, I want them both to be happy that this scheme can be satisfied. Okay, so this is clear for minimizing assumption. The truth is, even for black box, if you use the underlying scheme in a black box manner without relying on any properties, that means you can instantiate it with many possible assumptions, even if in the future somebody else will come up with a new assumption by which to build semantically secure public key encryption. I would immediately automatically have stronger public key encryption without needing to assume any algebraic property. So for example, a good example of it is all this. There's a new wave of results in crypto based on hardness of learning and random codes, and they don't tend to have the nice algebraic properties that the number theoretic constructions used to have, and still we could use them. Okay, so we could get new constructions with more assumptions. And finally, black box constructions tend to be much more efficient. We are not sure if this is something inherent to black box constructions, or just because we don't know any better, but the fact of the matter is the constructions that we have that are non-black box are much less efficient. They typically involve some kind of an NP reduction, Cook-Levin reduction. They're very heavy. Non-black box reductions often have some kind of ciphertext size that depends on the computational complexity of the underlying scheme. And black box constructions are much more efficient. All the black box constructions we know are much more efficient. So these are my motivations for doing this. Okay? Oh, this one backwards. Okay, so that's basically it for the general view of my talk. So what I'm going to do now is talk about these different bullets, define what is the goal that we want, what are these stronger attacks, and say what we can achieve, and maybe touch upon the technical details depending on your interest. Okay? Okay, so the topics for which we'll show constructions of strong public key encryption, I'll start with showing non-malleable encryption, so from semantic security to non-malleability. Then I'll talk about chosen ciphertext attack security. Then I'll talk about adaptive security. And I just wanted to mention, but I'm pretty sure I won't have time, to talk about tampering, security against tampering attacks or leakage of the key. Okay? And I didn't list all my co-authors because there are many, it's many different talks, but I'll mention them as I get to those results. Okay. So, so let's start with just defining more clearly what semantic security is. So in order to define, before I define semantic security for public key encryption, I just want to say the general structure of how we define security for cryptographic protocols is as follows. We need to define two things, right? We need to define the adversarial model. That means, so I want to build a system. When is it secure? So one, I want to say which attacks am I going to protect against? Okay, this is one of the things I want to improve. So that's the adversarial model. That includes, I don't know, the adversary's polynomial time or just linear time or whatever you want, what he can see, what access limitations he has. So that's one. And two is what the meaning of security is, okay? Namely, what should the adversary do for me to consider my system broken? Okay, so these are the two main components. And once we define it, we need obviously to design protocols. And the way the proofs go for such protocols, so first of all, we want them to be efficient. And then the provable security means that as long as the adversary is limited as in 1, then no break as defined in 2 is possible. Okay, and that tells you exactly what you can get for sure and exactly what you cannot get. Okay, this gives no guarantee of what happens if the adversary goes outside the model and is not restricted as in 1. Okay, but it gives you full security when, for this adversarial power, okay, and for this meaning of security. So obviously we want security for, we want to achieve security for an adversary that's as strong as possible, where the notion of security is as weak as possible. Like we want even the smallest thing to be considered a break, and we still want to achieve security. That clearly will make our scheme stronger, and we want the computational assumption to be as weak as possible, as I said before. Okay, so that's some general crypto stuff. When applied to public key encryption, so we'll define public key encryption as follows. We'll have, so this is mostly for notation. We'll have public key encryption will be defined by 3 algorithms. G, the key generation algorithm that generates public key and secret key, using some randomness that gets randomness as an input, generates public key, secret key. Encryption algorithm will get the public key and a message and some randomness and generate a ciphertext. And the decryption algorithm would get a secret key and the ciphertext and will give you back the message. Okay? This is public key encryption. And for semantic security, we assume that the adversary Eve is just eavesdropping and sees everything that goes on, sees the public key and sees the ciphertext. Okay? So now how do we define security for this, for public key encryption? So first we want to define the power of the adversary, as I said, and then we want to define what it means to break the system. So the power of the adversary, here are some typical common definitions. So perhaps not the weakest, but the weakest one that people use is adversary that can have chosen plaintext attack. What is chosen plaintext attack? An adversary that simply sees the public key. For public key encryption, seeing the public key, you can generate yourself as many encryptions as you want. So it's called chosen plaintext because you can choose whatever plaintext you want, encrypt it, and you see the encryption. Okay, so this is what the adversary can see for chosen plaintext attack. Chosen ciphertext attack says the adversary not only can see encryptions of his choice, he can also see decryptions of his choice. Okay, he gets some temporary access. Yes? So in this talk, I won't even talk about the difference, but everything I say is true for both of them. It's just that I'll have both negative and positive results. So for negative results, it's stronger to state them with CCA1, and for positive results, it's stronger to state them with CCA2. So I didn't want to mention it. But yeah, CCA1 or CCA2, it depends on when did you get access to the decryption oracle. But this is a stronger adversary, right, that can actually access the decryption oracle and ask, say, here's a ciphertext, what is the decryption? Here's another ciphertext, what is the decryption? That's a stronger attack. And even stronger ones, these are less traditional, are adversaries that can read some of the key, part of the key, maybe all of the key, or adversaries that can change the key in an arbitrary manner or in some specific manner. Okay, so these are different adversarial powers. And now we also need to define what is a breach of security. So there are many ways to define a breach of security. And one of the first things people think about is, oh, recovering the key would be a breach of security, right? That's obviously a breach of security. If I have a public key encryption scheme and the adversary, whatever power we give him, CCA, CPA, can see what's going on and recover the secret key. That's clearly a breach of security. But defining this is not good enough because there are other things the adversary could do. So say maybe I have great security, the key can never be recovered. Still, the adversary could possibly recover the message that was encrypted. That's also clearly a breach of security, right? And what if the adversary can't recover the message that was encrypted, but instead could figure out if two encryptions, two ciphertexts belong to the same message or not? Well, for some applications, this is no big deal, fine. But for other applications, this may be a big breach of security. Okay, and as I said, we want to define a breach of security the weakest way we can achieve so that we can use this in many applications. Okay, so this underlined one is the one that is the one chosen for semantic security definition. Okay, so for semantic security definition, a breach of security is being able to recover any information whatsoever about the message. Okay, so semantic security is if you can prevent an adversary from recovering any information whatsoever about the message. Okay, so no matter whatever he knows in advance, seeing the encryption doesn't give the adversary any extra information. So this is equivalent to indistinguishability. An equivalent definition is to say if the adversary sees an encryption of 0 and an encryption of 1, the adversary cannot tell which is which, even if he knows for a fact that this encryption is either of 0 or of 1. Okay, and it turns out that it must be randomized. So any questions so far? This is old. This is semantic security. Any questions? Okay. So I'll show an example because I'll use it subsequently in several stronger definitions. So EIGamal public key encryption, here's how it works. I'll go quickly over it. So for key generation, the public key is P, G, and H, where P is a prime and G is a generator, and H equals G to the X mod P, and the secret key is X. Okay. Then to encrypt a message M, you take a random R, and you take G to the R and H to the R times M. That's anybody can do the encryption. And to decrypt, when you get a pair, one is G to the R and one is H to the R times M, supposedly you do just C2 over C1 to the X. And if you check it, it works. Okay, if you have the secret key X, the algebra works. So this turns out to be in CPA is the same as semantically secure. This notation refers to the indistinguishability, that's semantic security, against chosen plaintext attack. So this turns out to be secure, semantically secure. So against chosen plaintext attack, this is totally secure because when the passive adversary can only see the public key, PGH, and the encryption, G to the R, H to the R times M. And it turns out if you assume some assumption called the Diffie-Hellman assumption, decisional Diffie-Hellman assumption, you get security. Okay? So I'm going to use this as an example later. Okay. So, so this can provably, and it's not too hard to prove, provably secure, semantically secure. But this is not good enough, and I wanted to demonstrate why. So one particular way for a stronger adversary to break it. So think of an auction example, okay? So one way to do an auction, I'm simplifying here, but one way to do an auction is each bidder sends their bid, encrypted, and then the seller chooses the highest bidder or whatever algorithm he wants to use, okay? So if we use EIGamal for this, for encryption, which we know is semantically secure, so it leaks no information. This encryption leaks absolutely no information to the adversary, knows nothing. So the first bidder sent his bid, that's the EIGamal encryption, G to the R, H to the R times the bid, right? The bid is the message. The second bidder, let's assume, is corrupted, is the adversary, okay? We said before this is semantically secure, so he has no idea what bid 1 is, no information whatsoever about bid 1. Nonetheless, it's very easy for him to bid twice as much. Okay, he would just take, this is all mod P. He would just take the second element and multiply by 2, mod P. Okay, very easy. That immediately generates an encryption of 2 times bid 1. Okay? So this guy, the second bidder, managed to bid 2 times bid 1 without knowing anything about bid 1, without breaking any security definition. All the security, the semantic security still holds. But this shows why it's not good enough, semantic security, for this application. It is good enough for some other application. Okay? So with EIGamal, with other encryption scheme, with RSA, with all kinds of encryption schemes, you can do similar things. They're called malleability. So this gives rise to another requirement we want to have, at least in some settings like auctions. We want the encryption of 2 messages to be independent of each other. Even if you see some encryptions, you want not to be able to generate any other encryptions that are similar to it. Okay? And this is called non-malleability. So that's the first type of stronger scheme we'll talk about, non-malleable encryption. So this was initially defined by Dolev, Dwork, and Naor, and there are several iterations of this. But basically, the definition is, given some encryption, it's infeasible to generate any correlated ciphertext of the encryption. Okay? So if, for example, if you have an encryption of M, you shouldn't be able to generate an encryption of 2M. Okay? So indistinguishability and semantic security are the same. So the way this is stronger definition is, in the previous definition we had in semantic security, we wanted to say that the adversary's output will be the same no matter what she got, whether she got an encryption of 0 or an encryption of 1. For non-malleability, we want her, even if she doesn't know what encryption she got, we don't want her to be able to generate any other encryption whose decryption depends on what she saw. Okay, so the decryption of what she gets looks the same no matter whether she saw an encryption of M0 or M1. So I can give you formal definitions. Do you want them, or should I skip them? Skip them. Okay. So that's the definition. Non-malleability is stronger. It always implies indistinguishability. And notice that there are 2 things. One is what attack you get. So we'll talk about chosen plaintext attack. And in chosen plaintext attack, it's not clear whether indistinguishability is strictly weaker than non-malleability or not. Okay? These are 2. So for chosen ciphertext attack, it turns out it's not trivial. It's a result. It turns out that for chosen ciphertext attack, it's the same. Being indistinguishable is sufficient to get non-malleability. But for chosen plaintext attack, it's not clear. And this is the question we'll ask. Can you use indistinguishable, can we use semantically secure encryption, which is indistinguishable under chosen plaintext attack, to get non-malleability, which we want? Okay? So in other words, can we immunize any semantically secure public key encryption against malleability attack? Okay, and for this question, most of the results I'll show, I'm focusing on questions where the answer is yes. We have results where the answer is no, but most of the things I'll show will be focusing on the yes. So the answer is yes, we can do it. So this is based on all kinds of work, but the last one is joint work with Seung Geol Choi and Dachman-Soled and Hoeteck Wee. And here's what we do. So starting from semantically secure encryption, so you have GED, we'll use it in a black box way to generate non-malleable encryption. Okay? So if you give me an algorithm for key generation, for encryption, and for decryption, I'll give you an algorithm for key generation, encryption, and decryption for a scheme that achieves a stronger level of security, okay, of non-malleability. Yes?
There's a difference in the way you interpret this result, right? So here you're saying that you're given this, then you can construct another one, which is an MCP.
Yes.
Whereas in the previous one, for CC2 case, if a scheme is IND CC2, then the same scheme, you don't have to move.
Yeah, that's a very good point. So in all my talk, when I say, does this imply that, I'm thinking, I'm kind of repeating the question as I'm answering it. In all my talk, when I say this implies that, I'm talking in terms of complexity theoretically. If you give me this scheme, can I change it, massage it, do some other scheme that achieves the other thing? I'm not talking about, if you give me a scheme and you prove A, can I prove B for the same scheme? Okay? Now, so because for semantic security, this is not true. For example, we saw an example, EIGamal is semantically secure and is not non-malleable. Okay? But the question is, can I change EIGamal to be non-malleable? Or can I change in a black box way, any scheme you give me that you prove for me semantically secure, can I show you what to do with it in order to get non-malleable encryption? And this is what the answer is yes for. And you're right about the CCA2, that in CCA2 they're equivalent even for the same scheme. But that's not the definition I'll use here. Here I'll use, is there a transformation? Is there any way without? So I'm talking about the complexity. I don't want to add any extra assumptions. And I want to use it in a black box way. I can't hear you?
There was another paper by Abi Shalat and Vinod and Russell Pass.
Yes. I'll talk about it, or not really talk, but I'll mention it. I'll have it. So I'll answer your question quickly. They don't have it in a black box way. And it's less efficient and it's non-black box. That's the short answer. OK. So our key generation algorithm and encryption and decryption, our key generation algorithm of the new scheme we'll call the key generation algorithm of the old scheme. The encryption algorithm and decryption algorithm will each call the corresponding algorithm in the underlying scheme and also the key generation algorithm. OK? So this is how it works. I mean, this is the statement of the result. I didn't show you how it works. So this is exactly the same as the next scheme. The next scheme is word heavy, and this is picture heavy, but it's going to be exactly the same thing. So this is just to have like an official statement of what we do. So assume you had a semantically secure encryption scheme, then there exists, you see I'm not saying it's the same scheme, I'm saying there exists another scheme that is non-malleable encryption scheme. And this notation means it's black box. Okay, it calls the other protocols in a black box way. Okay, and this is obviously the minimal assumption necessary because non-malleability implies semantic security, so you must have some semantic security. So our main technique is so this result existed before in a non-black box way, and there they used there's some issue of zero knowledge. In all of these non-black box techniques, there's some issue of zero knowledge, which I'll say in short. If you don't follow, it doesn't matter. But in general, sometimes when you have some scheme and you want to achieve a stronger scheme, one way to do it is to somehow run the first scheme and on top of it run some zero knowledge proof to prove that you're doing things correctly. And that typically is extremely inefficient, okay? Because these proofs usually go through some complicated NP reductions. And not so complicated, but like we use some statement, we say it's an NP statement, therefore it's reducible to 3 colorability, therefore we'll do something. Okay, so that's highly inefficient. So our main technique here was over using previous work, our main technique is to manage to verify consistency of encryptions in some zero knowledge way, but without using the inefficient zero knowledge. Instead, we use some error-correcting code techniques. Okay? Good. So this is a picture. So the red one is our result, and this is a picture that mentions the result you mentioned before. This is kind of a picture of what was known before. If you don't know any of these results, it's better probably that you ignore this slide. But if you know some results, this puts it in context of what was known before. So in CPA semantic security, we showed that it implies non-malleable CPA, okay, in a black box way. Before that, it was known in 2006 by Paz, Shalat, and Vaikuntanathan, showed how to do it in a non-black box way. Okay? And the way this graph is done, the CCA2 is a stronger definition than non-malleable CPA. Okay? And in fact, we knew already what we knew how to the best result in terms of assumptions, in terms of most general assumption. The best result we knew for how to achieve CCA2 was in fact already from DDN, the left work Naor. But they did it, first of all, with extra assumption. They couldn't do it directly from semantic security. They needed some extra assumption for zero knowledge, and it's also very inefficient. Okay? So now we did it in a black box way and with fewer assumptions, but we didn't quite get to CCA2. We only got to non-malleability. Okay? So, So at this point, I can take a detour and explain the construction for you. That will probably not leave room for... So I don't know what you prefer. Would you prefer me to go into detail on one construction so you understand what's going on? And then I'll go to these details, and I will not describe any other results, but you'll understand the idea of how we did this. Or I could go on and tell you a statement of 2 other results. So any preference? Should I go to the details, or should I? Go for the other results. OK. So, yes. Sure.
So In PSP, as far as I remember, they use semantically secure encryption to construct a designated verified proof.
Exactly.
Right? And it's not a NISIC. And
exactly.
Semantic security does not imply trapdoor permutation.
Exactly.
So you cannot construct NISIC using semantic security. So
right, and I can't either. You see, I'm not claiming that we can.
So in what sense the result is non-black box?
Oh, but it's non-black. The designated verifier non-interactive zero knowledge that they use is non-black box. It uses Cook-Levin reductions. They basically build designated verifier non-interactive zero knowledge for some NP language using some reduction. So it's not black box in exactly the same way that this is not black box. Yeah, any other questions? Yeah.
This is probably outside the mathematical domain.
Sure.
But given a sufficiently strong man in the middle, I can never tell who I'm talking to, because I can always talk to the man in the middle who's talking to the other side. So there's got to be something in the proof that doesn't cover this case.
So, I mean, you cannot prevent a man in the middle that just takes what, let's say you're the man in the middle. If you take what I sent you and you pass it on, right, it's the same as if I passed it. But this protects me from, if I send you something, this protects it from you changing into anything else that's dependent and passing it on. So I can prevent direct passing. In many cases, you can say it's fine if you man in the middle, if you directly pass and you don't change what I said. And this would prevent you from changing what I said. But yeah, it's a question of even, all the digital goods. It's like, how can you prevent, this is not really about what I'm talking about here, but in general, even like copyright protection. I mean, you can always copy, it's just digital stream, you can always copy it. What can you do? So it's kind of similar to that.
How does Alice know she's dealing with Bob and not with Bob Dash?
Right, so you need to assume something. The answer is, so first of all, it's a very good question. It's a big problem in crypto. I guess the simple answer is, you need to assume something, like you assume you have a public key infrastructure and she believes the public key. And that's why public key infrastructure is a big deal, and that's why it has to be very public and very available and very easy to verify. There are certification authorities. It's a big question in crypto in general. Okay, so to summarize this result, we indeed achieved non-malleability. Non-malleability is the level of security you need for things like auctions, where you want independence. Okay? Next, we want to ask about chosen ciphertext attack. Can we protect against chosen ciphertext attack? Okay, and I remind you that chosen ciphertext attack is the attack where the adversary gets temporary access to the decryption oracle. Okay, so can give ciphertext and get decryptions. Obviously, if she can give a ciphertext and get the decryption, she knows the decryption, because the decryption oracle gave it to her. But what we want to prevent is we want to prevent her from getting anything else. Okay, so if there is a specific ciphertext you want to decrypt, we want her to not be able to decrypt it, even if she can submit any other ciphertext that she wants to the decryption oracle. Okay, that's chosen ciphertext attack. It's a very important problem. In crypto, it has many applications where if you can break the chosen ciphertext attack security, that your system would not be good enough. And the question is, can we construct it from semantically secure public key encryption, okay, without any extra assumptions, in a black box way or in a non-black box way, whatever way? And the answer is we don't know. That's the ultimate answer. I don't know. It's a big problem, big open problem. If anybody can solve it, it's very interesting in crypto. Whether black box or not black box, if there's any way to take semantically secure encryption and build or show that it's hard to build CCA secure encryption, it will be very interesting. But I'll tell you what we do have, which are two partial answers. So one answer is everything I just said that I didn't show you the details of, the same construction can in fact be used pretty easily to achieve bounded CCA security. What is bounded CCA security? You remember that CCA security, chosen ciphertext attack security, is when Alice can access the decryption oracle. So if you knew in advance that you can access the decryption oracle no more than this many times, no more than n times, and you want to protect against that, if you knew that in advance, then you can build an encryption scheme that protects against up to n access to the decryption oracle. Okay, so this is bounded CCAs. If you know a priori what's the maximum number of times you could access it. Okay, so if this is how you define, if you define bounded CCA, then we can in fact construct it from semantically secure public key encryption in an easy extension of the result I mentioned before, I just mentioned, of the non-malleability. Okay, that's actually not hard to extend the non-malleability result to bounded CCA. Yeah.
Will the resulting protocol be practical in any way?
Be practical in any way. So let me think about how to answer it. So first of all, it depends what the a priori bound is. One thing that's not practical, I'll tell you why it is practical and why it's not practical. One thing that's not practical is if you know the a priori bound, the sizes of your new public keys and the sizes of your ciphertext and everything would depend on that a priori bound. So if you know that you will access it many times, then you need like long public keys. In that sense, it's not practical. There is a dependence, and the dependence is not great. It is practical in the sense that it's all linear. The number of times you call the underlying scheme is linear. So at least theoretically, it's practical. It's more practical than, definitely way, way, way more practical than DDN, say. Okay, so it's the most practical one from the general assumptions. It's not as practical as Kramer-Shoup. Okay? Okay. Good. So this is the yes answer. Now, what about general CCA? When people define CCA, they don't talk about bounded. They talk about, you don't know how many times you'll access it. So for general CCA, we kind of have an answer of no. Okay? What does it mean? Kind of. So this is another paper. We showed that in fact, for non-bounded CCA, you cannot take semantically secure encryption and build a CCA secure encryption in a black box way. Okay? So we almost show that. I'll give a caveat in a second, but we want to say that given a semantically secure encryption, can you use it in a black box way to build CCA? Okay? And when you want to say that the answer is no, there's a whole line of work separating cryptographic primitives called black box separation results, where you show that you can't do it in a black box way. Okay? So we kind of showed that you can't do it in a black box way. Why do I say kind of? In fact, we didn't show it for any possible black box construction. We showed it for a large class of black box construction called shielding black box construction. What does it mean? I'll tell you what it means. Remember, you start from GED, that's assumed to be semantically secure, and suppose that I could build a new G prime, E prime, D prime that are CCA, either CCA1 or CCA2. It's all true for both of them. Suppose from GED I could build G prime, E prime, D prime. So I'm saying this is not possible if the construction is black box and if my E prime never calls D. Okay, that's what shielding means. There's some technical thing saying the new encryption algorithm doesn't call the old decryption algorithm. Okay? So as I said, the real question of whether you can do it is still open. So what about non-shielding reductions? I don't know. I used to have this conjecture that you can't, but I'm not going to stand behind it. Like, we really don't know, and it's an interesting problem. Okay? Good. So you know what? I won't go into any details, because then when I finish the talk, if there is time, which there might be, then I can give details about your favorite result. And if there's no time, I won't. Okay? It seems better to me. Okay? So this is the same with a picture. We show that there's no black box shielding construction from CPA to CCA2. In particular, it shows that CCA2 is really stronger in some inherent way than non-malleable encryption. Okay? Good. So I'm basically done with my first two bullets. But all I did is describe what the result is and state the result. So if you have any questions about these first two things, feel free. Let me just say in one sentence, for non-malleability, we said we can do it, we can achieve it. It's a good construction, it's fairly practical. And for CCA security, we can achieve limited, and we have some negative results for black box constructions that are shielding. Okay? The next and last one I wanted to describe to you is regarding adaptive security, is a little bit of a change of gears. So really, this is a good time for questions about the previous stuff. Okay, so now I'm going to talk about trapdoor simulatable public key encryption for adaptive security. So why is this a change of gears? What's the change of gears? So first of all, so far I talked specifically about public key encryption. Okay? And I didn't really motivate why we need public key encryption, because I think you all know that. But what I'm going to talk about next is not really public key encryption. I'll have public key encryption as a tool. But my ultimate goal that I'm talking about now is secure computation, secure protocols among multiple parties. Okay, my concrete result will be specifically about public key encryption, but only as it's used as a tool within multi-party computation. Okay, so that's one change of gears, and the other change of gears will be that my ultimate result will use some extra assumptions, not just semantic secure encryption. Okay, so let me quickly talk about secure computation. So I'm talking about secure protocols. There's a bunch of parties. Now, it's not necessarily encryption where I want to send a message. It's more there's a bunch of parties. They want to compute something. They want to compute it securely. I won't go into the definition of it because I'll really only talk about the public key encryption part. But I'll talk about the attack model. So a non-adaptive or a static attack model in a secure protocol is where the adversary in advance, let's say you are all participating in a secure protocol and I'm the adversary. A non-adaptive case is where I will decide, OK, I'll break into you and into you and into you, and that's what I'm going to do. Whereas an adaptive adversary is one where I will be like, OK, I'm only breaking into you. Let's see what's going on. I'll see some messages, and based on the messages, I'll decide, OK, now I want to break into you. OK, so an adaptive adversary is one that, as the protocol is ongoing, in the middle of the protocol, may decide who else to break into. Okay? And adaptive security is more difficult to achieve than for static adversary. There's even some precise meaning to this, more difficult, but I won't go into it. And it turns out that all previous protocols that achieve adaptive security for arbitrary corruptions means if the adversary may corrupt more than half of the participants. If the adversary may corrupt more than half of the participants, there was no known protocol that achieved it in a black box way. Okay? From any underlying general primitive. Okay, so the only known protocols were non-black box and very inefficient for adaptive security. Okay, and moreover, they all used something called non-committing encryption, which I won't define, and it doesn't matter what it is if you don't know what it is. They all use non-committing encryption, but the only assumptions, concrete assumptions we knew how to instantiate non-committing encryption with was RSA and CDH. Basically, it's computational Diffie-Hellman. Basically, the only assumptions we knew how to instantiate adaptive security from were either factoring, like RSA, or Diffie-Hellman, that's discrete log related. Yes?
After 30 years, are there any other live public key schemes that accept these two?
Are there any? Yes. So first of all, there's elliptic curve stuff. That's one line. You asked about what other types of assumptions there are.
And the CDA doesn't work for elliptic curves?
Oh, it might work for elliptic curves, actually. It's weird. There's another one with a DDH. It might work for elliptic curves. You're right. And other assumptions that are kind of starting to be popular today is lattice-based assumption and learning-based assumptions, which are kind of related. So there's learning with error, or parity with noise, or random codes. All these things that I'm saying are kind of the same. They're different variations of the same assumption, and they're all related to lattices. And one good thing about them is that, at least for now, these new assumptions, we don't know how to break even with a quantum computer. These we know how to break with a quantum computer. That's one example. And in general, just having more assumptions is good. Yeah?
There are also some cut-and-choose protocols which only use...
I can't hear you.
There are also multi-party computation protocols which only use cut-and-choose techniques for Gauss-Garbut circuit, like Lindel's protocol, Lindel, Linkas, and...
Yeah, they don't achieve adaptive security. They didn't achieve adaptive. There are protocols achieving adaptive security if less than half of the parties are corrupted, or if more than half the parties are corrupted, but they were non-black box. At least this is true for as of when we did our result, which is, in fact, actually very new. It's going to appear in EIGaCrypt this year. OK. I mean, this kind of combines two results, but one of them appeared in TCC last year, and one of them will appear in EIGaCrypt next year. OK, so here are our results. So first of all, we define something. This I want to define for you because I think it's a good primitive. If you ever design anything else that's even unrelated to this, it's a good primitive to use, I think. Something called trapdoor simulatable public key encryption. This is where the public key encryption theme comes back in. So we'll define trapdoor simulator public key encryptions. We will show it's basically depends on previous work as well. This just using previous work. We will show how they can be used in a black box way to achieve adaptively secure protocols for any functionality. And we will show how to construct this trapdoor simulatable public key encryption from lattice-based assumptions and from factoring. Oh, so you asked about RSA and CDH. It wasn't known, for example, based on factoring. RSA and factoring is not the same, right? So now we did it also based on factoring, and also based on lattice-based assumptions and other things. So what I want to do is define, it's just basically define what trapdoor simulatable public key encryption is, because I think it's a useful primitive to know. We kind of invented it, but it's a variation of something that was known before, and I think it's a useful one because even, trapdoor permutation is the most useful, the most, common primitive that people use. Even that, we don't know how to do based on discrete log-based assumptions. We don't know how to do it based on learning. So this is, I think, a new, good, general primitive to use. OK, so I'll define trapdoor simulatable public key encryption. And that's it. Then I'll just state the results. OK, so here's the definition of trapdoor simulatable public key encryption. If you didn't follow the last part of the talk, it doesn't matter. That's a new definition. OK, we will use it for adaptive security of protocols. OK, so what is it? It's a regular public key encryption, semantically secure public key encryption, plus two properties. These two properties are very wordy, but are easy to explain, and I'll show an example. It's easy to explain them. So the properties, let me say the first one, one property is oblivious sampling. What is oblivious sampling? So in a regular public key encryption algorithm, the key generation algorithm generates a public key and a secret key. Right? So oblivious sampling of the public key means there's a way to generate a public key that's distributed exactly the same without, in fact, knowing what the secret key is. Okay? Can you generate a public key where you don't know the secret key? Okay? This needs to be defined exactly, but this is what it is. That's oblivious generation of the public key, and also oblivious generation of a ciphertext. What is the easiest way to generate a ciphertext that's distributed correctly is, OK, take a random message and encrypt it. You get a ciphertext. Okay? Oblivious generation says, can you generate a ciphertext without knowing what message it belongs to? Okay? That's what oblivious sampling is. This property is easily achieved for some protocols and is already known protocols of public encryption, immediately an immediate property that already exists, and is hard, or we don't know how to do it for some other public key encryptions. Okay? So that's oblivious sampling. And the second property is trapdoor invertibility. What is trapdoor invertibility? So let's say you generated the public key correctly with the key generation algorithm. You have a public key and a secret key. Can you claim that you generated the public key randomly without knowing the secret key? That's the invertibility. If I generated it correctly, but then I want to pretend like I generated it using the oblivious generation algorithm, can I do that? Okay? So I think it's hard to understand from this. Let me just give an example. It's much easier to see with an example. Let's see the EIGamal example. So this is what I wrote before. That's the standard EIGamal encryption. I'll show you that it already has these properties. Okay? So recall in EIGamal encryption, the key generation, the public key is P, G, H, and the secret key is X, and P is a prime, and G and H are generators. H is G to the X, mod P. Okay? And encryption, so let's do the key generation first. So an oblivious key generation would be very simple. You would just choose P, G, H at random. So P, you would generate a prime, choose a G at random, H at random. Sure, H is equal G to the X for some X, but you don't know what X is. We don't know how to do it. So it's very easy, and this is distributed the same, because G and H are basically random. Okay, so it's easy to see that it has this oblivious key generation. It also has oblivious ciphertext generation, because the real encryption, if you want to encrypt a real message M, you choose a random R, and you do G to the R and H to the R times M, right? That's the real encryption. But if you wanted to generate it obliviously, you just choose random elements in the group, C1 and C2, okay? Because H to the R times M is random. So if you choose a random C1 to C2, this is a valid encryption, but you don't know of what. Okay, so EIGamal easily has it. And these are also invertible. What does it mean invertible? Let's say I generated something correctly. So I chose P and G and H, and I know the secret key. I can always lie and say, oh, I chose H at random. I have no idea what the discrete log is. Okay, so EIGamal satisfies it. I'm giving you these examples. I won't go far with any technical details, but I just want you to explain what this assumption is, trapdoor simulatable public key encryption. Now, for factoring-based public key encryption, it's not as easy. So I wanted to give you an example where it's not obvious how to do it. For EIGamal, it's obvious. You just choose everything at random, and it's the right distribution. So for example, for RSA or for Rabin public key encryption, what is the public key? You choose n, that's the product of two large primes, p and q. That seems hard, at least it's not obvious immediately how to choose a number that equals the product of two large primes without knowing what the large primes are. Okay, it seems hard. So this means that the oblivious key generation seems hard to come by. Okay, not clear how to sample. So this is what oblivious key generation is. We also want to talk about oblivious ciphertext generation. So for example, if the ciphertext in Rabin cryptosystem or in other cryptosystems, the ciphertext often involves finding a square, for example, mod n. Okay, so how do you find a random square, mod n? Or sometimes it's part of a longer ciphertext. I'm kind of cheating because Rabin, like m square mod n, is not really an encryption scheme. It's more a trapdoor permutation, but it doesn't really matter. Even in the public key encryption schemes based on it, you always have to choose a random square. So how do you choose a random square? Well, it's fairly easy, right? You choose a number and you square it. That's a random square. But then you know the square root. So how do you choose a random square without knowing the square root? That's not obvious, okay? Because we don't really know how to test whether a number is that's considered hard. So this is something that doesn't that doesn't have oblivious key generation, okay? So this is the definition of trapdoor simulatable public key encryption. Is public key encryption that does have those properties that you can generate the public key obliviously and you can generate the ciphertext obliviously. Okay, if you know what enhanced trapdoor permutations are, it's kind of very similar to that. So this is the same definition that was before. So we didn't invent this. This was given by Damgaard and Nielsen. They defined simulatable public key encryption, and we changed it a little bit. But what did we get from it? Here's a summary of how. So I told you this has all kinds of things I didn't define and I will not define. But I told you we start from trapdoor simulatable public key encryption and we get malicious multi-party computation. This is a multi-step process. The pink ones are our results and the gray ones are not our results, and all of them rely on other results. But the bottom line is, so after we defined trapdoor simulatable public key encryption, on one hand we showed how you can achieve them from all assumptions that we know, from factoring, learning with error, that's lattice-based assumption, DDH, RSA. We showed how to construct them, and then using them, we have a sequence of results that leads you to malicious multi-party computation for any, all in a black box. That's a big deal that it's all in a black box. Going through non-committing encryption, I didn't want to define it because it's too many definitions, but if you care, I think you care about non-committing encryption. So the first result just shows how to get non-committing encryption from trapdoor simulatable public key encryption in 2 rounds, okay, optimal round. And once you get it, we already know how to get oblivious transfer from it, from previous work. And then we showed a compiler going from semi-honest oblivious transfer to malicious oblivious transfer in a black box manner. Yes?
With that one, how can you have a trapdoor for the OGen, where you generate something totally random and...
Yeah, so the trapdoor invertibility is this. It's not that you have trapdoor, but the trapdoor invertibility is this. Let's say you generated it not at random, not obliviously. You generated with the key generation algorithm, with the secret key. Can you lie and claim that you generated in the OGen? Okay, so if you have the trapdoor invertibility means if you have the trapdoor, if you have the secret key, can you come up with randomness to then lie and say, here's the randomness I used and here's how I got it? So for the example I gave for EIGamal, it's trivial. Yeah, if you chose P and G and then you chose X and you did G to the X equal H, and then I come to you and say, how did you choose it? You're like, oh, I flipped random coins and I got G, and I flipped more random coins and I got H. You don't have to tell me you chose X and did G to the X. That's invertibility even without trapdoor. Anybody could do that. Trapdoor invertibility is if you have the secret key, you can claim that you generated it obliviously. Because in all these algorithms, it will be used somehow. There will be some simulator that will choose it in this way. We'll choose everything in the correct way, but we'll claim to have chosen it obliviously, and we'll need to explain it. OK, so I won't go into this. Something about in the UC setting or not in the UC setting, ignore it. Let me just summarize all the results. I'm exactly on time, so after the talk is over, I can give you details on whatever you want if anybody wants to talk to me. Here's a summary. I talked about many things. So here's a summary of the results that I showed. So first of all, we showed from semantically secure public key encryption, without any further assumption, we can achieve non-malleability and bounded CCA. And we cannot achieve full CCA for shielding black box constructions. And we also showed from semantically secure public key encryption with this extra property of oblivious generation, trapdoor simulatability, we can build non-committing encryption and from it adaptively secure protocols for any functionality against an adversary that can corrupt as many parties as he wants. Okay, the results I didn't mention, I keep mentioning them just in case you want to ask me afterwards, is we have both positive and negative, both possibility and impossibility results for some physical attacks like key tampering or key leakage. Okay, and I think that's it. Yeah. Okay. Any more questions? Yeah?
What was the definition of non-committing encryption?
So the definition of non-committing encryption is an encryption where it's a regular encryption, semantically secure encryption, with an extra property that, so in encryption you have encryptions of 0 and encryptions of 1. I might have a slide on this. Let me see for 1 second. No, it's not here. Oh well, I'll tell you the definition. So it's a regular encryption. In a regular encryption, you have encryptions of 0 and encryptions of 1. And they're disjoint, right? And everything is either encryption of 0 or encryption of 1. Non-committing encryption is where encryptions of 0 and encryptions of 1 are not really disjoint. There's some small set of things that could be either encryption of 0 or encryptions of 1. And where if you encrypt correctly, you want to encrypt a 0, you encrypt a 0. You want to encrypt a 1, you encrypt a 1. You're extremely unlikely, almost for sure, you'll never hit something in the intersection. But if you're a simulator or if you're some special party, you could generate them from the intersection. So basically, non-committing encryption is when, if I'm not the right party, I'm just cheating, I can generate something that's an encryption that later I can prove that it was an encryption of 0 or prove that it was an encryption of 1. And this is used as a tool for all existing results that achieve adaptive secure encryption. Yeah. Any other? Yeah? How do I define oblivious sampling?
Or time-coordinates.
Yeah, did I not define it? So oblivious sampling. Oh, how do you define this? I don't know the secret key. What does it mean that I don't know the secret key? That's a good question, yeah. Because I can always say, oh, choose secret key, public key, and then forget the secret key. And that will not be good enough. So the way I define it is I define that the scheme is still semantically secure, even if I chose the public key. So let's say I chose the public key with this oblivious way. I want that if I have all the random coins that were used to choose it, so I have an algorithm, OGen, gets some random coins and generates a public key. I want that even if I have the random coins that told me how I generated this public key, the scheme is still semantically secure. If I get an encryption, I have no idea how to break it. Whereas if you generated it in the naive way of generating a secret key and a public key, it's not secure, right? Obviously, you can decrypt anything.
You give the random coins and the public key?
An external party, or you can think of it as an internal party that generated it using the oblivious generation algorithm. So if you generated, I'm just answering you about the key, but it would be the same thing for the ciphertext. So you want both of them. For the key, you want to say that if I generated the key using OGen, that means I got a key, like for example, for EIGamal, I generated P, G, and H. And that's how I generated them. I chose a P correctly, and then I chose a random G and a random H. Okay? Then now if you give me some EIGamal encryption, it's semantically secure. I will have no idea what you encrypted, okay? Even though I know exactly how I generated them with the OGen. And the same so that's for the key, and the same for the ciphertext generation. So, for example, if I chose a message and square it and got an M squared, then then it's not semantically secure. I know what the square root is. So you want it to remain semantically secure even if you chose it like this. Okay, we have a definition, and Damgaard-Nielsen had a definition. I can show you. I probably have it. I can find it in a slide. I'll show you after the talk. Somebody else had a question, I remember. You? Yeah?
The only use you seem to make of the public key nature is that chosen plaintext is a passive attack rather than an active attack.
Yes.
And now it's got to be critical, because if you use a one-time pad, it's totally semantically secure and it's totally malleable. So
yes.
Where do these proofs break when you use when you apply them to a one-time pad? They go to break.
Yeah, I see your question. That's a good question. Let me see. Hold on a second. Wait. Let me find. I kind of wanted to show this. This is our construction, and you can ignore all the details. But the way so this PK, you have some encryption scheme that's semantically secure, and you want to build non-malleable scheme out of it. So the way you do it is some way of choosing many pairs of keys. Okay, in some way, it doesn't matter. I'm just showing you to. I'm trying to think how to. So you generate. So the way you do it is by repetition. Basically, the way you do it is you generate many public keys of the underlying scheme, and you encrypt the same thing many times using these public keys. With one-time pad, this construction won't work because. So it's not that the security won't work. You can't even encrypt. Let me think how to say it.
No.
It's not, no, it's private key encryption, and it is very malleable. You're asking why if I apply this, whatever construction we have, if I apply it to a secret key encryption, will I get...
To that particular one,
Yeah,
yes.
you know, we might... You see, we actually might get non-malleability when we apply, because when we apply our construction, it will no longer be one-time pad. It will be one-time pad repeated many times with some extra proof of something, with some extra cut and choose, because we don't use the same scheme. We change it. So in fact, our construction will work also for secret key encryption. Yeah?
I was wondering if you could say more about how to use the chapter simulatable PKE stuff for the multi-time computation.
Yes. So the truth is, we don't use it directly. There are two stages there. Sorry. So there are two different stages. Tell me which one you want me to elaborate on, or both. First, we use trapdoor simulatable public key encryption for non-committing encryption. Okay, that's one construction, and I can show you how to do it. And that's not really related to adaptive security. So it's just non-committing encryption is what I was answering before. Non-committing encryption is that you have some special way to generate ciphertext that can be opened both ways. Okay, and I can tell you how, just intuition, how to use trapdoor simulatable public key encryption to generate non-committing encryption. Okay, that's one aspect. And another aspect is how to use non-committing encryption for adaptively secure computation. And that's another aspect. So I think you're asking more, the second one. Okay, how to use non-committing encryption for, the way you do, so let's assume you have non-committing encryption. Non-committing encryption is something where you can generate ciphertext that you can open either way. So the way to do it is the following. So let's say we have a secure computation protocol, okay, that we know is secure for non-adaptive adversaries. Okay, so we all run the protocol, and we know if the adversary knew in advance who it broke into, it was secure. How do we get adaptive security? So what is the problem with adaptive security? The problem with adaptive security is the adversary is here, and he sees what's going on. And he saw the message you sent him, and based on that message, he decided to break into you. He saw that message, and he's like, aha, this is your message. I want to break into you. Okay? Once he breaks into you, you have to show him, oh, I forgot to say, we assume no erasures. Achieving adaptive security is easier if you assume that you can safely erase. Everything we do, we assume you don't erase anything. So let's say I'm the adversary. I saw you sent, I didn't break into anybody yet. I saw you send some message to him. It's encrypted. I can't read it. But based on the message, I decided to break into you. Once I break into you, now you're corrupted. I tell you, show me what message did you send, what randomness did you use, how did you generate that ciphertext from your message. Okay? The problem is, when we want to achieve security, we have a simulator. We want to, to show security, we want to show that in the ideal world, a simulator can simulate everything. So before I broke into you, the simulator just generated something. That's easy. Just generated an encryption of anything. All the encryptions look the same, so it's no problem. So the simulator could generate an encryption of 0. It looks the same as the encryption of whatever it is you really sent to him. But the problem is once I broke into you, I see your input, and I have to explain what you sent him with what you really have. And this is where the non-committing encryption will come in, is the simulator will send something that could be opened both ways. And then if I break into you, I can see what you committed to. The way I described it now is kind of a little cheating. What I described now is exactly how it was defined, non-committing encryption by CFGN, Canetti, Fagan, Naor, and Goldreich. Okay, they define non-committing encryption exactly in the way I described it to you. They used it in exactly this way to simulate secure channels. You know how if you forget about adaptivity, we can assume we have secure channels, and then in reality we don't have secure channels, so we'll use public key encryption instead. So for adaptive, they use non-committing encryption instead of secure channels, and this is exactly how it worked. It turns out for this setting, the standalone setting, in fact, at the end, there's newer results that don't even need any non-committing encryption. They used it for if the adversary only breaks into few people. Anyway, the way I describe it to you now is it's used now for the UC setting, for example. It's used in somewhat more sophisticated ways. But the intuition is the same. It's supposed to simulate a secure channel where I first saw what was going on, and then I broke into you, and now I need to explain, and I can't change my mind anymore. Like, this is the message that was sent. Now I have to explain this message as an encryption of what your real inputs are. So that's how non-committing encryption is used there. Yeah?
Can you expand this little gray standalone one-way function?
Yes, I can. OK, these are our results. So we built from semi-honest, oblivious. So we built non-committing encryption, and it's already known by close. It's Canetti, Lindell, Ostrovsky, and Sahai showed how to use non-committing encryption for semi-honest OT. Okay, and then for semi-honest, we show the compiler that goes from semi-honest oblivious transfer to malicious oblivious transfer. But our compiler doesn't really not use anything else. It uses some ideal commitment functionality. Okay, so you would ask, you were cheating all along. You were saying you don't want any extra assumption. What is this extra assumption that you're adding here? Commitment. So this extra assumption can be achieved in the UC setting with some common random string or some other setup. But what I wrote before is, in the standalone model, it's not really an extra assumption because commitment comes from one-way function. So we can remove it completely because even if you had just public key encryption, that already implies one-way function, already implies commitment. So in fact, it does not require any extra assumptions. So, yeah?
Can you go a little bit into the trapdoor simulable PKE construction for RSA and what it looks like in particular? Or you've got it?
Yeah. Yeah, let me think.
What's it look like?
Yeah. Let me see. Let me see for a minute. Is this the right thing? How to construct trapdoor simulatable public key encryption based on hardness of factoring. That's kind of what you're asking, right? I specifically said that it's hard to construct this oblivious sampling for factoring-based stuff, right? So what are we going to do? So let me think about what the most important parts are. So there's the generation of the public key, and there's the ciphertext. The ciphertext, let's say, is x squared, and the public key is n equals p times q. Okay, and we want to generate them both. So how do we do it? It doesn't have anything. So first of all, so we'll change the scheme. So first of all, we'll say we want to allow any integer n. It doesn't have to be the product of two primes. Okay. Once you say that, we know how to. It's not easy, but we know it's not trivial, but it's a known result of how to sample random integers with their factoring. Okay. So so now I'm changing it so that any n is fine, even if it's not p times q. Okay. So that's easy. I mean, we'll still need to show that some security holds and that something happens. Okay. Now, another problem is it was important that squaring was a permutation. If you know Rabin works on quadratic residues. Now, once I change the n to be not necessarily p times q, it's no longer a permutation. So we change the domain. Instead of quadratic residues, the domain is all the, not quadratic, but a to the 2 to the k. Okay, we somehow change the domain. All these are like number theoretic theorems, but they're easy to prove. The hard thing was to notice how to do it and to decide to do it and to figure it out. So you can show that squaring is a permutation over this domain. Okay, k is specifically the length of n. Okay, so you can show it's a permutation. Good. N is hard to invert the same way that Rabin is hard to invert for n equals p times q. So, I mean, not the same. This is, Rabin says that if n equals p times q, it's hard to invert. So now I define the scheme for any n, but the hardness to invert is only on n equals p times q. That's fine because that's a sizable fraction of n's. Okay, I'll manage to use it. Okay, so this shows you that squaring is now, I got a weak trapdoor permutation. Okay, weak in the sense that it might be easy to invert if n doesn't happen to be equal to p times q, but if it does, then it's hard. Okay, so that's one change we did. Okay. I mean, there's many details. Let me think. Okay, so at the end of the day, what I'll do is I'll choose many n's, and I'll choose enough n's so that I know that it's very likely that at least one of them happens to be a Blum integer. So we don't know how to generate Blum integers n equals p times q, for p equals 3 mod 4 and q equals 3 mod 4. So we don't know how to generate a Blum integer without knowing the factorization, but we can generate just a bunch of random numbers, enough of them such that they're dense enough such that one of them is likely to be a Blum integer. Yes?
At the current security, it looks like about a million or a billion little bits, right? If you have 160-bit numbers, you have a million. If you have 1,000-bit numbers, you have a billion.
You're just doing k to the third.
Yeah.
Yeah. It's true. Yeah. I guess. Wait, no, there was more detail. So anyway, this is the oblivious generation. I feel like this doesn't answer your question, right?
Let me tell you where I was trying to go.
Yeah.
So I wanted to understand if the construction that you had for factoring, or for RSA, in particular, took into account or could take into account the fact that when we tend to typically use RSA these days, there's formatting inside of the way the message gets encrypted, right? We don't. When you think about it from a number theoretic perspective, we think about taking m and we exponentiate. We don't worry about the format of m. But when we use it in practice, there's all of this padding and randomization that happens, which it seems would interfere with your ability to generate the appropriate oblivious sampling, right? Because you have to be able to oblivious sample something that's a ciphertext.
Right. I see what you're saying.
So that's kind of where I was going, and I understand these are different constructions.
It won't interfere, and I understand your question. It won't interfere because we also don't, we theoreticians also don't use RSA as it is, because that's not semantically secure even. So in practice, the way it's used is some paddings of specific format, whereas in theory, the way it's used is this, using a hardcore bit. So, so it doesn't matter as long as if you assume that whatever way you use is semantically secure, then it will work. Okay, so it doesn't assume that it doesn't. The way the protocol works is like it generates a bunch of, I don't know, n to the fourth or some number of ciphertext where, not n to the fourth, sorry, n, some linear number of ciphertext where a quarter of them were chosen obliviously and a quarter of them were chosen correctly. You encrypted them, and 3/4 of them were chosen obliviously. You wanted the distribution of the oblivious to be the same as the distribution of the correct one. So this will be guaranteed if, I don't know if it's guaranteed for like ad hoc ways to construct RSA encryption, but it is guaranteed if you guarantee your thing is semantically secure, then I guarantee it will work.
Okay.
Yeah. Okay.